I thought I was recording the lesson. My apologies. So this is lesson number 5, and we are continuing on PowerPoint number 3, which is on the normal distribution. So we have an example here. Unfortunately, I forgot to start recording it, so I started it already. The normal tells us its shape, what it looks like. It looks like a bell curve. Mu equals 6.84. That's directly in the center, 6.84 by the peak. And sigma, 1.55, a measure of variability. Tells me how far I go left and right for one deviation. And we know that this point right here, these are the inflection points. Again, you don't need to know that term. It's a calculus term. But the inflection points tell me where one sigma is. It's the point where it switches from hill to bowl. What we say is concave down and concave up. Again, terms you don't have to know. And if you go twice as far, or 3 times as far, or 4 times as far, these curves, of course, go forever in both directions. So an example of something that is usually considered to be normal will be IQ scores. The average IQ score is 100, and sigma is 15. So if you score exactly 100, you're right in the center. And if you score 115, then 15 to the right, you're 1 standard deviation up. 85, you're 1 standard deviation down, and so on. Anyone know the highest ever recorded IQ score in history, unless it's been broken since years back?
Wasn't it 214?
I don't think it was quite that high, although it was close. 206, I thought it was. But again, this is 20 years ago, so maybe since then it has been broken. But her name was Marilyn Vos-Savant, and she had the highest recorded IQ score of all time. She had a column in syndicated column in newspapers and magazines called Ask Marilyn.
I think she got a 228.
Was it 228?
Yeah.
Could be. I'm going on my memory from 20 years ago. But even so, that is whatever. Once you hit 200, you're already off the chart intelligent. So but she wasn't infallible. In fact, there were some situations where she was talking about math where she was wrong. So, just because you're really smart doesn't mean you're never incorrect. In fact, Einstein, you guys ever hear of Einstein? Pretty smart guy, they say. So, even he was not always correct in physics, which was his you heard about him? Yeah, name comes up in conversation now and again. Okay, so anyway, so let's go back to what we're talking about. So if you give me, this is slide 10. If you give me those 3 things, you tell me that it's normal, you tell me the mean, and you tell me sigma, you have told me everything there is to know about the distribution, okay? Those 3 things tell me everything. I know the shape, I know the center, I know the variability. If you don't give me all those 3 things, then we could be talking about different situations. If you just tell me it's normal with the mean, but I don't know sigma, I don't know how sharp it is, how wide it is, how spread out it is. If you tell me sigma and it's normal, but you don't tell me the mean, I don't know where it's located. I don't know where the center is. And if you don't tell me that it's normal, it could be any shape. I might know the mean and sigma, but I have no idea what it looks like. So all 3 of those are really, really important. And this whole chapter is devoted specifically to distributions that have this shape, normal distributions. Why this shape above all other shapes? Because as we're going to see, every other situation is in some sense connected to this one, which makes it the most important of all distributions, the most important of all shapes. And we're going to talk about that later. It's called the central limit theorem, very important theorem in statistics. So let's now turn or flip or scroll to slide number 11. And 11 is a very important formula, theorem, name, whatever you want to call it. And it's one of my favorites because it's so obvious, right? It's not, doesn't have like a fancy, a fancy name like the fundamental theorem of calculus or the Taniyama-Shimura conjecture or Fermat's last theorem. It's called the 68, 95, 99.7 rule, so that you know exactly what to do and what numbers are appropriate. So what does it say? It says if you have a normal distribution whose mean is mu and whose standard deviation is sigma. So it says, look at the graph. Look at the really, really dark blue in the center. The dark blue is obviously not all of the graph. It still misses some on the sides, correct? So the question is, what percent of the entire graph is in dark blue? What percent is included if you go 1 sigma to the left and 1 sigma to the right from mu? Answer, 68%. 68% of the graph falls between this spot and this spot. So this portion right here is 68% of the entire thing. It's not exactly 68%. It's like 68.25 or so, but 68% is fine. Now, if you go 2 sigmas out, if you go 2 deviations left and 2 deviations right, obviously you get more graph. But notice that because the graph drops, it doesn't just double. It doesn't make sense. Oh, I have 136%. Doesn't make any sense. So you don't quite double. But what percent of the entire thing are you going to have if you go 2 deviations to the left and to the right? Who can guess based upon the name of the rule?
95.
95%. So 95% falls within 2 deviations. And if I go 3 deviations left and 3 deviations right, how much do I have now?
99.7.
99.7%, which means you pretty much get the whole thing when you go 3 deviations out. It's called the 68, 95, 99.7 rule. In the name itself are the 3 numbers that are appropriate: 68%, 95%, 99.7%. Now, those are not exact. Those are approximate numbers based upon a calculus-based technique, which we are not going to talk about or study. Those of you who had calculus, even you probably can't do it because it requires numerical methods of integration, which I don't think you've really would do much with in a first semester of calculus, or even 2. Oh.
That's in multivariable calculus, I believe.
No, it's still single variable calculus. Multivariable calculus would not cover. The problem with a situation like this, those of you who don't care about calculus, you can tune out for about 30 seconds. But those of you who have had calculus, the function which is appropriate for a normal distribution does not have an antiderivative. There's a branch of mathematics called differential Galois theory, which proves that it does not have an antiderivative, and as such, well, let me be more specific. There's no nice functional form of an antiderivative, but there are still approximation techniques like the Riemann sums that you can do to get an approximate value, or more sophisticated approximation techniques, and that's really the best we can do. But anywho, back to our regularly scheduled broadcast. We now are dealing with a situation where we have these 3 numbers, and we can use them to calculate areas. So let's scroll down to the next slide. Not too far. I don't want you to see any answers or anything like that. So about halfway down the slide, make sure it's covered after that. It says the distribution of Iowa Test of Basic Skills, or IPS, vocabulary scores for 7th grade students in Gary, Indiana is close to normal. Remember, no real distribution is ever precisely normal. That was a few slides ago, but they are approximately normal. And for the sake of this exercise, we'll just say they are normal, right? Hello, Martin's friend. Welcome to the class. Does your friend want to join us? Martin?
Oh, no, he's just interrupting. Sorry.
Oh no, I thought maybe he wanted to learn some math. I want everyone to learn as much as possible. It's fine with me.
No, he knows that I'm supposed to be focusing on this, so.
And he's bothering you anyway?
Yeah, he is.
What a bastard. All right, so unbelievable. You know what? Put him on speaker I want to talk to him.
Okay. Sam
Hey, you, Martin's friend.
wants to talk to you.
Hello, Martin's friend.
Hi.
Hi, leave him alone. He's learning math.
Okay, I'll leave him alone.
Okay, thanks. Okay, and we're back. So the INTBIS score is approximately normal. Look at the notation, by the way, that we're introducing. It's n parentheses 6.84 comma 1.55 n parentheses. What does that notation tell us?
The mean and standard deviation.
Exactly. It actually tells us three things, right? N tells us that we're dealing with a normal distribution. Bruh, bruh, bruh. Okay, bruh. So N is telling you that it's a normal distribution. 6.84 tells you what the center is, and 1.55 tells you how spread out it is. Okay. It says sketch the normal density curve for this distribution. We already have it on the board. And the question is, what percent, don't look at the answer or anything. I know what bruh means, bro. Everyone knows bruh. Although I find it interesting that we would use more letters than the actual word instead of less. Like nicknames are supposed to be shorter, right? You know, so bruh is like 4, you know. Well, I did sound confused. I didn't know what he meant by bro. Like, was he talking to me? Was he talking to someone else? I just didn't know what he meant. Right, bro? Right? Anyway, so.
But sir, what was the 6.84 and the 1.55? What is the again?
6.84 is the center, it's the mean. And 1.55 is the standard deviation. Come on, bro. You know that. Does that make sense?
Yeah, the
okay.
Yeah.
So now you're welcome. So now we have the question: what percent of scores is between 3.74 and 9.94? This one's easy, or should be easy. What percent of scores is between 3.74 and 9.94?
95.
95%, right? 2 to the left, 2 to the right, in between, 95%, immediate. Well, the next question is a little tougher. It says, what percent of scores is above 5.29? What percent of scores is above 5.29? I want you to think about this. Okay, you don't need anything except for the 68, 95, 99.7 rule, but it's not as simple as the last question. You actually have to think a little bit about it.
I'm assuming it's 95.
It's not 95. 95 is 2 to the left, 2 to the right.
Well, I mean, because the way I'm looking at it is if you go like 4 standard deviations to the right, that's still the same amount, right?
No, because every deviation to the right is less and less area.
Oh, yeah, right.
Because the graph drops, right? So it's not enough to say 4 is always the same, because if you shift that 4, it can be completely different values. Agreed?
Yeah.
Can we assume, since it's a normal graph, that it would be that if we wanted to get one section of the sigma, that we could just half that percentage?
Sure. It is symmetric.
So it wants to know like the percent that's above 5.29, so all the way to 9.94, all the way
No,
to
all the way,
11 point.
all the way to infinity, all the way to the end.
Oh.
Not just 9.94, all the way to the end.
I have a question.
Yeah.
Isn't there a way you can put it in your calculator?
Yes, we haven't learned that yet.
Oh, okay. Never mind.
Yes. Yes, 100%. And your calculator will be even a better approximation than what we're doing here. But we're trying to do it without a calculator just to show you that it's possible. So who has an idea? No. Nobody? Even if it's wrong, I have no clue. I love it. No clue. I'm not sure how to do it. I love that answer. Totally fine. But I want you to think. I don't want you to give up because you don't know how to do it. Sometimes
So
it strikes.
Would it be around 84%?
It would be 84%.
Yeah, right. Because the 5.29 to the right of it, you still have the 65 that's in the middle, right? And so then what we do is, since we're already not going to the left, we're not going 2 deviations to the left, we're taking half of the other 95, which would be 13, and you add those together, right? Or sorry, not 13, 16. Does that make sense?
Yes, it does make
Okay.
sense. So let me do it in a couple different ways. Okay. So first of all, from here to there is what percent? What percent is between 5.29 and 5.29 and 8.39? 68%, right? This is 68%. This is the 68, 95, 99.7 rule. So what is between here and there?
34.
34. It's exactly half. Right? Symmetry. Perfect mirror image. Whole thing is 68. This must be 34. Do we agree? How much is that? Does that help at all?
Is it 100 minus 34?
No. This is center forever. Center forever. How much is that?
Oh, it's 50 half.
That's exactly half, 50%. Remember, the graph is symmetric, which means the right half of center and the left half of center are both half of it. Agreed? So this is 34% and this is 50%. We want both together. How much is that going to be? How much is that going to be? 34%, huh?
89? 89%.
84%.
Oh, 84, sorry.
34 plus 50.
Yeah.
Does that make sense? Does that make sense?
Yes.
Now, here's another way of doing it. What's the inside part again?
68.
68%. So what's the outside of that going to be? If one to the left to one to the right is 68%, how much is outside of that in either end?
32%.
32%, right? 68 plus 32 is 100%, correct? Now that 30,
Yes.
that's 32%. Some of it's over here. Some of it's over here. How much is over here?
16.
16%. Well, I want everything except for this. I want that forever. So if I don't want that 16%, but I want everything else, what am I going to have?
84.
84%. So two different approaches for getting the answer. Does that make sense? How do I make my screen bigger so I see what you guys are looking at? Spotlight video. So that makes sense, right? Yes?
Yes.
Okay. So let me ask you another follow-up question. How much is between 3.74 and 8.39? How much of the graph is between 3.74 and 8.39? I want you to think about this. Don't just give me an answer. I want you to think about it. We good? I love it. Okay. Think about that. Use the same logic. 3.74 to 8.39.
Isn't it the same amount?
As
Wouldn't
what?
it be 84?
Why?
Well, because we're using the same logic, right? We're still taking the 65% from the one deviation each, right?
Well, 68%, you mean?
Or sorry, 68%. Yeah, my bad.
Okay,
I keep thinking 65. 68%, right? And then we're taking half of what that 95 part would be, right? So you're taking the one standard deviation, or I guess the second standard deviation, which would be the 3.74, right?
Okay. So keep
So that would be the 16%, right? And so then we
no,
would add those
no,
together.
no. 16% is forever.
Is it
Oh, okay.
76%?
16% is from here forever. We're stopping there.
Okay.
I'm stopping there.
Is it 76%?
Nope, not 76%. It's good. Thinking about this is good.
Would it be 81.5?
It would be 81.5.
Right, because we're stopping at the 3.74, so we're ignoring the deviation. That's the 2.19. Okay.
So let's explain what he did. First, two full deviations. So from here to there is what percent? Two deviations left, the two deviations right is what percent?
95.
95%. One deviation left to one deviation right is how much? %68%, right? This is the 68-95 rule, correct? Yes? Communicate, please, yes?
Yes.
Okay.
Yes.
So that means that this part here and this part here together is how much?
$32?
No, not 32.
Oh.
68 plus this has to equal 95.
27.
27%.
Oh, okay.
Which means this part here is how much?
Whatever 27 divided by 2 is 13.5 is what someone said.
So 13.5%. Someone said that? Yeah, 13.5%. So what do we want? We want this part plus this part. This one we know is 68%. This one we know is 13.5%. So when you add them together, 68 plus 13.5 is 81.5%. So you can use the 68, 95, 97.7% rules to get lots of different things if you recognize the symmetry of the situation. Does that make sense what we just did? Questions on it? It's good so far, right?
Yes.
Okay. So now let's move on to the next topic, which is slide 13 on standardizing. Standardizing is a very important concept. Oh, that doesn't work at all. I don't know how to get rid of that. That'll work. Okay. Standardizing is a very, very important idea. Basically, what you do is as follows. So I'm going to erase what we have on the board and put up a new situation. So suppose you have the following. Give me a center, any number. Make it simple, please.
4.
How much?
4.
4, okay. And now give me a simple sigma, a simple deviation. How about 1? So if I go 1 to the right and 1 to the left, I get, you know what, this is a little too simple. Make it 14. And make my, so this would be normal of mean 14 and sigma 3. A little more complicated. I think the way I was doing it originally was too easy. Too, not easy, but it wouldn't illustrate what I want to illustrate. So 14, what's this one going to be?
17.
17. How about this one?
12. I mean, 11.
11. That's 1 deviation out. If I go a second deviation, what's this one?
20.
20. What's this one?
9.
I guess we're better at addition and subtraction, huh? That's 8. And then 23, I'll give you one more chance. What's this?
5.
5. Okay.
5.
And it goes on forever, of course, in both directions. So what we want to do is we want to be able to compare 2 different distributions that have different means and different sigmas. How do you compare 2 different distributions? They're going to have different centers, different deviations. Their numbers could be all over the place. What we do is we standardize them, which means we make them all the same. How do we do that? By the following formula. Z equals X minus mu over sigma. Very important formula. The Z-score is equal to the data minus mu divided by sigma. Let's see what we get by doing a few examples.
Professor,
Huh?
can you repeat what standardizing is again?
So standardizing is a method by which allows us to compare different distributions that have different means and different deviations. So we make them all essentially the same so that they're easier to compare to each other. For example, suppose you and your friend are taking different classes at CSUN, and you take a class and you get an 80 on a test, and your classmate gets a 60 on their test. Who did better, you or your classmate? You scored an 80 and your classmate scored a 60. Who did better?
I mean, we don't know if that's like a percentage, or we don't know if it's like 80 out of 200 and like a 60 out of 60. You know?
Fair enough. Let's say they're both out of 100.
All right.
Okay. So you scored an 80 out of 100, and your classmate scored a 60 out of 100. Which of those two grades would you rather have?
80.
Oh, I forgot to say one thing. When you scored an 80, everyone else got 100. And when your friend got a 60, everyone else got a 0. So you scored 80 when everyone else got 100, and your friend scored a 60 when everyone else got a 0. Which would you rather be?
80.
Well, it depends. It depends. Is your professor grading on a straight up 90 and above, 80 and above, 70 and above? Or is your professor grading on a how well you do compared to the rest of your class? When I used to teach physics, grades are notoriously extremely low in physics. 30s and 40s are usually the average grade on a test. So I always told my students, the way it works is I grade you relative to your peers. If you are in the top 10% of the class, you will get an A. If you're in the next 20%, you will get a B, and so on. So I graded it based upon your grade in comparison to how the class did. So if you get an 80 when everyone else gets 100, you have the worst grade in the class. When you get a 60 and everyone else gets a 0, you have the best grade in the class. Which means that if you're taking classes on this kind of a grading scheme, you would rather have the 60 than the 80. The only way to know that is by calculating their z-scores. I mean, of course, I made the numbers obvious. 60 relative to 0, 80 relative to 100. Yeah, okay, it's obvious, but sometimes it's not so obvious. What z-scores do is they compare different situations so that you can tell immediately which one is better. That's the idea of a z-score. We'll illustrate it with an example, a few examples. Let's start with this one. So z is your z-score, x is your data, mu is your mean, and sigma is your standard deviation. So let's start with the middle data point. Let's say you get a 14 as your middle data point. These are your x values, your data values. Let's compute your z-scores for each one of them. What's your z-score for 14? What would your z-score be if your data was 14?
1/3.
Well, plug it into the formula. What's x?
14.
What's mu?
14.
Okay, what's 14 minus 14?
0.
Okay, what's 0 over 3?
0.
Okay, so your z-score is 0. Let's plug in 17 for my data point. What's my z-score?
1.
Plug in 20. What's my z-score?
2.
Plug in 23. What's my z-score? Anyone? What's your z-score if you plug in 23?
3.
Huh?
3.
3. What's my z-score if I plug in 11?
-1.
-1. How about 8?
-2.
-2. How about 5?
-3.
-3. So what do the z-scores tell us? The z-scores don't care what your actual data is. Your z-scores tell you how many sigmas you are away from the mean. If you're 1 sigma from the mean, or 2, or 3, or 1 this way, or 2 this way, or 3 this way, or you're at the mean, the numbers are much more easily decipherable. If I tell you that your z-score is 2, you know exactly where you are in relation to the mean. You are 2 standard deviations above the mean. So if I'm comparing 5th grade test scores and 6th grade test scores and 7th grade test scores and so on, obviously the different grades are going to learn different ideas, correct? They're in different grades, correct? They're not all going to learn the same thing, right? But if I say, oh, this student fell in the 90th percentile, what does that mean, the 90th percentile? What does the 90th percentile mean? If someone falls in the 90th percentile, right? Oh, my child is so smart, they fell in the 90th percentile. What does that mean?
They scored a 90 or higher.
No, it does not mean that, because 90 or higher assumes that you know details of your actual score.
It means that only 10% of students scored lower than him.
Higher than him. Not lower, higher. If you're in the 90th percentile, that means only 10% scored higher. It means you were better than 90% of your peers. You see how that's different than what you said?
Yes.
Okay. Yes, it's the majority, but more specific. Hello. Nice.
Do anything else?
Another burger. No, I'm kidding. I'm kidding. I mean, I'm not kidding, but I mean, are you making more or just a
We
one?
only have 4 buns.
Just a one then.
Okay.
Thank you so much. I really appreciate it. No, that's
There's
perfect.
plenty of meat.
It's perfect. Thank you. More meat? What do you mean more meat?
Well, like we have enough meat for more burgers. We just don't have any more buns.
Oh, but you have bread. Like that? Oh, okay. Yeah. So, is that okay?
Yeah.
Okay. I'll take like 3 or 4.
Okay.
Dad? Okay. Anyways, guys, oh, you gotta show the food? That's my burger right there. Yeah, that's what I'm talking about. So, yeah, the rule here is I buy the steak and they do the cooking, and it's a perfect relationship and everyone's happy, right?
Yes.
Everyone's happy.
Because I'm poor, but I can cook.
Exactly, and I'm rich, but I can't cook, so it works out perfectly between us. Anyway, so I highly recommend this situation. But I'm poor, but I can cook, and I'm rich, but I can't. So I should take lessons. But anyways, shit, where were we? Yes. So Z-scores, so percentile. If you're in the 90th percentile, that means you are better than 90% of the population. But notice, I don't know what that means, but I'll take it as a compliment. Notice I don't know anything about my actual scores. Percentiles just talk about you in relation to everyone. Oh, you're in the 90th percentile? You're better than 90% without knowing anything about the individual scores. It's the same thing here. If your Z-score is 3, you are scoring 3 standard deviations above the mean. Where? What's my actual score? No idea. Not relevant for the problem. Because knowing your Z-score tells you where in the curve you fall. Does that make sense? We'll certainly do some examples of it. In fact, let's start with the example on the next page. Next slide. This is slide number 14. It says, the heights of women aged 20 to 29 in the United States are approximately normal, i.e. normal, with a mu of 64.2 and a sigma of 2.8 inches. So that means that the average 20 to 29-year-old female in the United States is how tall? How tall is the average?
64.2.
64.2, right? And okay, and if a woman is 70 inches tall, 70 inches tall, is she abnormally tall, would you say? Is she average? Is she close to average? Let's compute her Z-score. How do you compute her Z-score? You take her data, which is 70, and then what do you do with 70? How do you compute a Z-score? Once you have 70, what do you do with it?
Minus it by the mean and divide by the standard deviation.
So let's go ahead and do that. 70 minus the mean, divide by the standard deviation, what do you get?
2.07.
How much?
2.07.
Okay. So you got 2.07, which means where do you fall in relation to all other 20 to 29-year-old females in the United States? You fall 2 deviations above the mean, approximately, right? 2.07, let's round the 2. So that means what percent of females from 20 to 29 in the United States are you taller than if you are 70 inches tall?
Two percent.
Sorry?
2%.
2%, huh? Let's see if that makes sense. You fell here, right? At 2? Right? 2 deviations, right?
Approximately, yeah.
Okay, so you're taller than all of those. Is that 2% of the distribution? Is that 2% of the distribution? Does that shaded part, don't have to be sorry, you're answering. It's okay, you're learning. Does that look like 2%? No, it's, okay, so certainly closer to 95%. But it's not 95%. I want to give me a more accurate answer.
98.
Is that just because you picked a number more than 95? Or do you have a reason why it's 98?
100.
I'm sorry?
100 minus 2 is 98.
But where did it get to? Oh, no, the 2 is not percent. The 2 is where you fall on the number line. That's just where you fall. You fell at 2. You fell there. The percent's got nothing to do with that. So we need to find how much is shaded to the left of 2. So how do we do that? This is for everyone. What percent is to the left of 2? This is mine.
97.5.
97.5. Where do you get that from?
Well, if we do 3 deviations to the right and to the left, that's 99.7, right?
Yeah.
If we have 2 deviations from the right and the left, that's 95%, right? So in that little chunk between 95 and 99.7 is 2.5%. You get me? That should be 2.5% of the data.
Isn't it 2.35% of the data?
Is it 2.35?
Well, 95 to 99.7 is 4.7% more, right?
Oh, no, yeah. Yeah, so it would be 2.35% of the data. So you would add that on to the 95%.
Ah, okay, well, that's wrong.
Oh, okay, then I'm just wrong.
No, you're not completely wrong. Your first answer was correct. It is 97.5. But your reasoning was wrong. So that's what we want to clear up, because your reasoning.
So instead of adding it to the 95, I would take it away from the 99.7.
No.
Is that what I would do? Okay.
So I want to give others a chance to think about it. And then when I explain it, hopefully it'll be clear on your end as well. So again, we're looking for what percent is to the left of 2. And this is good. That's good stuff. Anyone? What percent is between -2 and 2?
$95.
95%. What percent is outside of that?
Isn't it 2.5?
Prevent
pregnancy
2.5.
and it won't impact your ability to get pregnant in the future. Finding yourself in the family planning aisle. No prescription or ID required. I've got this.
Can you hear me?
I can hear something. Hold on. So that wasn't me, right?
Nah.
Okay, it's already been muted, so I have no idea who it was. But whoever you were, let's never do that again, please. So what were you saying just now as your answer? Someone was saying it, but it was overridden by that noise, so I couldn't really hear it very well.
I don't know if it's my mic or not. Can you hear me?
Well, I hear some commercial. I hear something. Is that TV? What is that? Hello? Hello?
Yeah, it was TV, my bad.
Okay, because that was very loud TV. Okay, so what were you saying is the answer?
I'm sorry. I was saying, was it 2.5?
It was 2.5%. 95, which leaves 5% on either side. So on this side, must be 2.5%. 2.5%, 2.5%. So how much is to the left of 2?
97.5.
97.5%. So if a female between 20 and 29 is 70 inches tall, what percent of other females between 20 and 29 is she taller than?
Ninety-seven point 7.5.
97.5%. So would that make her abnormally tall?
Yes.
Yes, it would. In fact, the general rule of thumb is anything outside of 2 deviations is considered unusual. Anything outside of 2 sigmas is considered unusual. So because she's 2.07, she would be considered to be unusually tall.
But that could be good too for like a test score, right?
Listen, it's got nothing to do with being good or bad.
Yeah.
It's got nothing to do with being good or bad. Okay, there's no bad about being tall or short. Unless, I mean, listen, there are people out there who are so tall that it's actually a condition and something in their, what is it, their pancreas or pituitary gland or something. I don't know what it is. I'm not a medicine person, but there are conditions that make people grow abnormally, and unfortunately, usually they die very young or young-ish. But we're not talking about that. Unusual does not mean bad or good. Unusual just means exactly that. It means unusual. So the 97.5% represents that she is taller than 97.5% of her demographic of 20 to 29 females in the United States. 70 inches, that's 5'8". So once a woman hits 5'8", she's already considered unusually tall. Not bad or good, just the way it is. Now, 97.5% means that approximately 2 in 100 are going to be that tall. Right? 1 in 50 approximately. So 1 in 50 is not rare, but it is unusual. What if someone was 60 inches tall? If someone was 60 inches tall, where would she fall? Well, let's calculate her z-score. If she is 60 inches tall, then what is her z-score going to be? What is the z-score? Same situation.
-1.5.
How much?
-1.50.
-1.5, -1.50. So if someone had a z-score of -1.50, where would they fall on the number line?
They wouldn't be on the number line?
Well, everything's on the number line, right? Look at the number line, negative 1.5 with the z-score number line, not the data number line, but the z-score number line. Where would they fall on the z-score number line?
Between,
I'm sorry?
between 11 and, oh, I'm looking at the wrong thing. Between -1 and 0.
Between where and where?
-1 and 2.
Between -1 and 2, halfway between them, correct?
Yeah.
Okay, so what's important to realize is that a negative z-score means that you are to the left of the mean. A positive z-score means that you are to the right of the mean. If you had a z-score of -1.5, would that be considered unusual?
No, because it's not outside 2 deviations.
That's exactly it. You're not outside 2 deviations. You're within 2 deviations. The inside 95% is normal. The outside 5% is unusual. Does that make sense? Yes, no, maybe so? So in this case, the actual data is normal, 14.3. Normal with a mean of 14 and a sigma of 3. Z-scores are also normal, but they always have the same mean and they always have the same sigma. What is the mean for a z-score? Look at this. What's the mean?
0.
0. It's right in the center. And what's sigma?
1.
1. This is called the standard normal. It's the standard normal distribution. N01. When you compute z-scores, what you're doing is you're changing the original normal to the standard normal. The standard normal is a lot easier to work with because the mean is 0 and sigma is 1. Standard normal, a lot easier to work with. Let's look at the next slide. The standard normal distribution is the normal distribution with mean 0 and standard deviation 1. So, if a variable has a normal distribution of n of mu sigma, and you switch it to the z-score situation, you switch it to z, it will always be n of 0, 1. This is the huge advantage that we can have when you convert a normal to the standard normal. Because if I have 2 different normals, 2 different means, 2 different sigmas, they're all over the place. What do? No problem. Convert them both to the standard normal. Then you can compare them because they're the same distribution now. So the only way to compare 2 normals is to make them both the standard normal. When you do that, easy to compare. Does that make sense in general what I'm saying? If you have a question, speak up. Don't just sit there in silence and hope it goes away, because questions do not tend to go away on their own. Please, if you don't understand, say something. Okay, I can't see you nod because most of you are not on camera, or shake your head, or thumbs up or thumbs down, or the finger, whatever you're giving me. I can't see that. Okay, so I need some kind of communication on your end, preferably verbal or something.
Can you explain it one more time?
Say again?
Can you explain it one more time?
What is the it that you're referring to?
the combination of the two that you said, like how do you do that?
So if you have two different normals,
Right.
and you want to compare them to see which one is better or worse or higher or lower, whatever the case may be, you convert them both to the standard normal, because they have to be the same distribution before you can compare data. If I say what's better, 10 or 9, it depends. Maybe 10 is when the mean is 11, and 9 is when the mean is 10. I don't know. I don't know where it falls in relation to the mean. I need more info. But if you give me the standard normals for both, then they're the same, and I can compare them very easily. Does that make sense?
So, go ahead.
No, ask, speak, words. Words are good.
So the standard normal is when the n represents the symmetry of the curve.
Well, not just the symmetry, but the specific shape.
The specific shape.
It's the whole bell curve symmetric pattern is given by the letter n.
The 0 is the mean,
Zero is the-
and the 1 is the standard deviation. It's a sigma.
Right. So if you look on slide 15,
Mm-hmm.
that curve is an N01.
I understand.
Okay, because the mean is 0 and the deviation is 1. So no 6.84s and 1.55s and all these weird numbers. Okay, make them all N01s, and they're easy to work, or at least easier to work with, and significantly easier to interpret.
I just don't understand how we could convert a graph that looks much different than that into something like that.
And that's a great question. And unfortunately, statistics is very difficult to teach sometimes, because a lot of what we do cannot be justified, because the justification is too advanced. I cannot justify it. You just have to trust it. And that's the worst. And as a teacher, I hate saying that to students. You should never trust anything. Verify, always verify. But stats, it just can't be done, because the level of math required to verify is not this level.
At least I know I'm not missing anything.
No, you're just the opposite. You're getting something by recognizing that it's something that is an issue and should not just be glossed over. Oh, okay, sure, no problem. No, wait, why? You should ask that. I just can't answer it. I mean, I can't answer it and have you understand what I'm saying is what I'm saying. And it's not a knock on you. You just haven't had the math courses necessary for it yet.
Professor? So for an example, for that slide 15, if the 1 was a 2, would it be N02?
It would.
Okay.
But why would I create an N02 distribution when I can make an N01 distribution?
Right.
So
no, I was just looking for the example, like.
Yeah, I could. 100%. And the question is, what's so special about an N01? And the answer is as follows. First of all, it's very easy to interpret. If it's N01 and you fall at 2, you are precisely 2 deviations above the mean. That's what N02 tells us. Or sorry, N01, if your z-score is 2, you are 2 deviations above the mean. In the original one there, what point falls at 2 deviations above the mean? What data point would 2 deviations above the mean in the original one be?
20.
20, right? Because 14 is the center, 17, 20, correct? But if I just told you, hey, I'm thinking of a distribution and you got a 20 on it, you wouldn't know it's 2 deviations above the mean unless you knew the mean and the deviation. Then you can compute and say, okay, 14 plus 3 plus 3, oh, it's 2 deviations above the mean. But if I tell you it's the standard normal and your z is 2, you know exactly it's 2 deviations above the mean. That's a huge advantage that we have. The other advantage is as follows. Unfortunately, we can only do so much with the 68, 95, 99.7 rule. If I said 1.7 to 3.2, you can't really use the 90, 68, 95, 97, 99.7 rule. So we have to have tools that will answer questions that don't fall on nice numbers like those. And what we do is we have tables. And these tables have been created years and years ago, these tables of data. And since there's infinitely many normal distributions, we would, in theory, have infinitely many tables. But since I can change every normal to a standard normal, I only need one table that will work for all of them. I just need the N01 table. Because now all I have to do is convert anything to the N01, look it up in the table, and I'm done. As opposed to needing a different table for every single one. Every single mean, every single sigma, that's infinitely many tables. But here, convert them to 0, 1, look up one thing and you're done. That's a huge advantage. Now, nowadays, with your calculators, they can do anything. You just say, here's the mean, here's the deviation, I want to be between these two numbers, and it pops out the answer for you. But we didn't always have that. So we're going to learn how to do both. For now, let's turn, please, to slide 16. The cumulative proportion for a value x in a distribution is the proportion of observations in the distribution that are less than or equal to x. So usually what we work with is between this number and this number, between 11 and 17, between 8 and 23, and so on. The cumulative distribution or the cumulative proportion always means everything up until that number. That's a definition. So if I say what's the cumulative proportion up into 11, then that means what's everything up until 11, automatically. I don't got to say, oh, do you mean left? Do you mean right? No, cumulative. That means accumulate everything up until this point. Get everything up until 11, or whatever number you pick. And luckily, we have cumulative distribution tables. So what I would like you to do right now is as follows. I don't want to have one here on this PowerPoint. There's one in the book, but here's what we're going to do so that we're all looking at the same one. I would like you to do a Google search for the following: Z-score table. And I would like you to go to images so that we're all in the same one. And in the first row, go to the third, fourth, fifth, sixth, seventh, go to the 8th picture in the third row.
Can you share your screen instead?
You know what? That's even a better idea. That's even a better idea. I'll share my screen. So don't worry about it. I'll just share my screen. That's a much better idea. So hold on. Let me find a good. Okay, so let's go back. That's a great idea. Share my screen. Okay, so can you all see this? Yes, no, maybe so?
Yeah, we can see it.
Okay, so what we have here is a standard looking normal N01 table. Uses the letter Z, that tells you that it's a normal N01. And you have three things. You got numbers along the top, you got numbers along the left side, and then you have all of the numbers in the table itself. So again, top, left, here, let's annotate. How do I do this? Annotate, draw. So we got the numbers on the top. We have the numbers on the left, and then we have all the numbers in the table itself. And each of them means something else. So the first thing you always start with is the left side. What is your Z? So somebody give me a Z to 2 decimal places. Give me a Z-score to 2 decimal places. Just make one up. Give me a Z-score to 2 decimal places.
1.73.
Okay, 1.73. And the question is, when you have your normal, center 0, 1 deviation 1, 2 deviations 2, and you go to 1.73, the question is, what is the area to the left of 1.73? So here's what you do. You find in the table 1.73. So 1.7 is here. Agreed? So I know that this is the row that I'm going to be looking at. Which column am I going to use in this row? Huh? So I go up to the top. The top tells me the second decimal place. 1.70, 1.71, 1.72, 1.73. Oh, here we are. That's what I want, 1.73. So what's the area to the left of 1.73 in this example going to be?
0.9582.
0.9582. Okay, 0.9582. Does that make sense? So if you're ever curious on a problem, what is the total up into a value, not between 2 numbers, but from the far left up until some value, you find that value, you find its Z-score, in our case 1.73, and all you do is you go to a Z table. 1.73, where do they meet? 95.82%. Just to illustrate, if I take out my calculator, which is more accurate than the table, I'm going to stop sharing. So if I take out my calculator and I tell my calculator to do from negative infinity up until 1.73, so this is what I plug into my calculator. I tell it lower from negative 99999999999, essentially negative infinity, to 1.73, mu 0, sigma 1, enter. And what's the answer? 0.958184601, which is more accurate than the books or the table of 0.9582. Do you see that? Does that make sense?
If you ask this on like a test or quiz, would you give us the table or will we do it on our calculator?
Well, first of all, tests are open book, open notes, or anything like that. So you're more than welcome to have it. It's in the back of your book, or you can print out a Z table prior. And worst case scenario, you know, I mean, if you're not on video and you're not being watched, you can just go and do a Google search for a Z table and you get one as well. But by the end of the semester, we're going to learn how to do it on the calculator, so it's not even a problem. Because your calculators will do it for you and everything will be good. Does that make sense so far? Yes, no, maybe so? Speak.
Yeah.
So we use the Z table to find cumulative proportion. That's correct. Let's look at slide 17. This is just another example. In their example, they want the probability or the proportion of Z's less than 0.81. They want the proportion of Z's less than 0.81. So what they do is they go to their Z table and they find 0.81. Notice that 0.8's on the left and the 1's on the top, 0.81. And they look where the row and the column meets, and where they meet at 0.7910. So it's 79.10%. Does that make sense so far? Are there questions on that? Let's stop here before we get into the calculations. So we can do a lot of examples next time of finding values either from the table. I'll teach you how to use your calculator if you have one. But this is a good place to stop. It'll let you ruminate over the ideas. And next time we can just pick up from here. And remember, next time we have a quiz as well. Don't forget on the syllabus, right? Quiz at the end of the 3rd week. That's this Thursday. That quiz will be the first 2 chapters. And the way to work is I'm going to be on the, I'm just going to give it to you. I'll email it to you. And you guys can just do it and send it back. You're not going to be on video or anything like that. I'll trust you. Probably my first mistake. Won't be my last. But you know, you'll have X amount of time, and then you'll get it to me when you can. Preferably like within an hour and a half. I'll give you the time in class to do it. So we'll do a few minutes of class, and then I'll give you the guys a quiz. Sound good?
So it's not on Canvas. We're just gonna like write it on a piece of paper, scan it, and email it back.
That's correct.
All right.
And that's on Tuesday?
And that's on Thursday.
Oh, Thursday.
Yeah, remember, it's on the syllabus. Yeah,
Okay.
and you can. I'll give you the quiz. You can leave class. You can do it. Okay.
So I'm guessing we don't have class then on Thursday.
No, we do. Again, beginning of class, we'll do more normal stuff.
I just got up.
And then I will give you the quiz, and at that point, you can go. And no, it won't be due 11:59. No, it'll be due about an hour and a half after I give it to you. I'll give you like an hour and a half to do it. So you'll have, you won't even need it, because in previous semesters, I'd give them like an hour in class, and they all finish it. So I'll probably do the same thing, like teach for like a half an hour, and then give it to you and give you guys an hour to do it. I think like 20 questions, something like that, about 20 questions. And they're not hard, you know, some true or false, some fill in the blank, not fill in the blank, but true or false, couple short answer, you know, make a stem plot, you know, categorical, what type of graph is better, you know, nothing that we haven't done. I'm not testing you on deep understanding. I want to know if you understand the basics. Okay.
Professor, I have a question about office hours.
What?
I have a question about the office hours.
Yeah.
One, is it the same link as this Zoom? Like,
yeah. All day long, same one. Yeah.
And is it just, it's Mondays and Wednesdays only from 6:37?
No, most of it's Tuesday, Thursday.
It says on the syllabus, it said Mondays, Wednesdays, 6:30 to 7.
And what about Tuesday, Thursday?
After that, it just says TR 3:20 to 3:55 and
Yeah.
5.
Tuesday, Thursday, TR 3:20 to 3:55 and.
Oh, okay, and then 5 to 6:25. So
And
just
5?
ignore Monday, Wednesday.
Well, no, it's Monday, Wednesday also. Monday,
Oh,
Wednesday,
okay,
it's
okay.
this. Tuesday, Thursday, it's those.
Okay, cool, perfect.
Okay.
Thank you.
You're welcome. No, it won't be like the homework questions. It'll be more straightforward. I hope. You know, what I think is straightforward is not necessarily what you think is straightforward, but I hope. Okay. If you have any questions, if you don't have questions, you're more than welcome to go now.
I have a question about the test, actually. I know it's kind of early for this, but Will the test be on the program that we're using to do our homework?
I think so. I have to talk to my supervisor about that.
Okay, so you're not going to be making the questions. It's going to be the test.
So the questions are actually in a test bank. I'll be picking the questions, but I won't be making the questions.
Okay. Are they going to be some of the questions we had previously on our homework, or will they be completely new questions with options?
It could be completely new.
Oh, okay.
I mean, based on the same ideas, but it can be completely new.
Okay. Also, I joined the Zoom at 6:33, like 3 minutes after the class started, right? Before you started the lesson. And so I didn't get to say here when when you were doing the attendance.
Okay,
I've been here the whole time. Was wondering if you could go back into the attendance roster and mark me here.
Yeah, 1 second. Let me do that right now. What's your name, please? I'm not sure who I'm talking to.
April Montez.
April Montez, okay.
Yeah.
Oh, let me find it. Okay, you're good.
Thank you.
You're welcome. No problem. Yeah, closer to the PowerPoint. You know, kind of like just basic, do you understand what's going on? Yeah. Bye, Grace. Yeah.
I also came in late.
You came in late? Who am I talking to?
Yeah, Vanessa.
And when did you come in, Vanessa?
I came in like 6 minutes after.
After I began the lesson? Or
Yeah.
Okay, so
After you began the lesson.
I got to mark you late because that was the rule. But better that than absent, right?
Yeah.
Okay, thank you. Oh, yeah. Oh, yeah.
Hello, Professor.
Yes.
Let them go. I have a long question.
Okay. So,
Professor, real quick.
Yeah.
I spoke to you last time about my attendance real quick, and it still marks my attendance down, but I've been
Okay, who am I talking to?
to Oliver.
Oh, is this you talking about Thursday's class?
Just in general, because I joined a week later, and I talked to you already about attendance, but my grade is at a 67 for attendance,
Okay,
but I've been to everyone.
1 second. Oliver what, please?
Bitton, B-I-T-T-O-N.
Okay, so I have you as present on Thursday. And okay, so what day did you join?
I joined the second week of school.
So were you here a week ago today? Because I have you as absent.
I've been to every class since I joined.
Okay, so you were there that class.
Yeah. I believe I talked to you last week about it too. Maybe you just forgot or something.
It could be. I have so many things. Okay, I just changed it. It should update.
Okay, perfect. Thank you.
Okay, so it should be okay now.
All right, Professor. Have a good one.
You too. Okay.
Hey, Professor Berkowitz. It's
Yes.
Weston.
Hey, Weston. How are
So, barely keeping it together, but here I am trying. So the standard Z table is based off of standard normal, and that will tell us on that very simple graph that's on the PowerPoint slides.
Yeah.
At exactly which points will have which value on this standard curve, kind of like the unit circle in trig.
Okay.
Have I got that right so far?
I don't think there's a connection between trigonometry and this.
Sorry, that was silly. Just it's a very standard distribution, standard normal, and it's only used in we're only paying attention to the units of sigma, the mean being 0, all of that stuff.
Okay.
And the standard Z table applies to that specifically, the
Correct.
standard normal. And there is a way to convert some very real world graphs into the standard normal graph.
Well, most things that occur in nature are normal.
Okay.
Like heights, intelligence ratios, weights, pretty much anything that's just natural is going to be fairly normal in distribution. And every one of them can be converted to a standard normal distribution. That's correct.
Okay. And by converting them both into that standard normal and setting that midpoint at 0 rather than whatever it was before, we're able to compare two graphs that will probably look pretty similar since we're able to convert them into the standard normal.
Well, the thing is, the original graphs are both going to be normal,
Yeah,
but they're going to have different centers and spreads.
got it.
Okay, so they're going to both look bell curve-ish, but they're going to have different centers and spreads.
Okay, so
Okay.
we don't set the center to 0 with a
No,
graph.
we convert it to a different graph where the center is 0.
Okay,
And we do that for both of them. So then we can overlap them because now they both have the same center. And then what happens is we can see which one is more spread out than the other. We can compare them better that way.
got it. Okay, so we're altering some key things about the, not altering, but revaluing some key things in the graph, but they keep different spreads, if you will.
Yes, exactly. We're making, well, so again, let me rephrase. I think I just misspoke. The original two curves are both bell curves. They're both normal.
Yes.
They have different centers. They have different spreads. When we convert them both to the standard normal, their graphs perfectly overlap, not just center, but spread as well, because it's the same graph. The only difference is where we fall on that graph. So one might fall at z equals 1.7, and the other one might fall at z equals 1.3, and then it's very easy to compare them because everything's the same except for their z's.
Okay, that makes a lot more sense.
Okay. So
And then we can, and then, you know, percentage out of what or whatever
Yeah.
can get converted into, instead of like paying attention to that with different percentages of different values, we can just look like, okay, well, if they looked exactly the same, how many standard deviations from the center would those points be? And then we can directly compare percentages on different kinds of graphs that, you know,
Correct. That's exactly it.
that are bell curves. Okay, thank you so much. That finally completely encapsulated my question.
I'm glad to hear that. Okay, perfect.
Take care.
Okay, all right. See you on Thursday. And then we have the other ones.
Hey, Professor.
Yes.
I just had a question. Basically, I remember talking to you maybe about last week about my book situation. It's Anthony.
Yeah.
Yeah, I just received my book with the access code, and I remember you told me to call the CSUN bookstore to get the access code from them, but I called them and they said that since they sent the book already, they didn't have it or something like that.
Okay.
So I wasn't able to do any of the homework assignments, and I didn't know if they were due or not.
Well, the homework was pushed off till Thursday, so you have at least 2 more days.
Like all the previous assignments?
It's only been 2 so far, yeah.
Okay, perfect.
Yeah.
Okay, thank you.
You're welcome. Jane, Martin, Deshaun, and Rebecca. I'm going to stop recording.